This week's conversations are going to be centered around soil erosion control. President Roosevelt is quoted as saying, "A nation that destroys its soils destroys itself," in 1937. So, the soil erosion control portion of this class is discussed in Chapter 14. The page numbers might depend on the version of the book that you have. So just make sure you search for soil conservation and soil erosion um, in the in the table of contents. And if you love this topic, you should consider taking NREM 427, which is all about soil conservation and erosion control in the spring. It's only offered once every 2 years, so now's your chance. The learning objectives for this unit include understanding the causes of global land degradation over the last 50 years, comparing geological and accelerated soil erosion, understanding on-site versus off-site effects of accelerated erosion, list and describing the 3 steps in soil erosion by water, identifying the 3 main types of water erosion, differentiating among the conservation tillage systems listed in this PowerPoint, as well as in your textbook, define and understand the revised universal soil loss equation known as Russell. We're also going to talk about how conservation tillage affects soil physical, chemical, and biological properties. We're going to assess the effectiveness of various types of conservation practices and the mechanics of wind erosion and how we can basically control erosion for rangelands, forest lands, and construction sites. So first, I posed to you the question, is soil a renewable or a non-renewable resource? Take a second to think about that. Do you think soil is a renewable or a non-renewable resource? It's actually a non-renewable resource because 1 inch of soil can take 200 to 10,000 years to form, but humans can destroy 1 inch of soil in less than a year. In fact, we're destroying soil at significantly greater rates than it's being formed, and this is causing mass land degradation across the globe. This is especially concerning. So there's various forms of global land and soil degradation. The 3 main causes of land degradation, and remember these are a learning objective, are desertification, deforestation, and then soil degradation. So soil degradation accounts for about 56% being lost to water erosion, 28% due to wind erosion, and 12% due to physical deterioration, and 4% due to chemical deterioration. These things can be caused by overgrazing, deforestation, inappropriate agriculture practices, fuel wood overexploitation, poorly managed construction sites, anywhere where there's cleared soil that isn't protected from wind, water, or other sources of soil erosion. So first I want to say that erosion processes can be natural, but a lot of what we are seeing that is degrading Earth's surface is enhanced erosion because of man's activities. So there's natural factors such as rock type, wind strength and direction, rainfall, angle of slope, type of vegetation covering it, frost action, and the nature and properties of the soil itself. But there's also human factors like military training or recreation users, mountain bikes, horse riders, walkers, grazing livestock, farm vehicles or vehicles in general, bicyclists, and other type of activities. So the types of erosion that we're concerned about include water erosion, which is the removal of soil or rock by moving water, wind erosion, which is the removal of soil or rock by wind, and gravitational erosion, which is landslides, mass wasting, often related to water. So in geologic versus accelerated erosion, we have the fact that geologic erosion is always occurring without the influence of humans. Some really beautiful examples of natural erosion include the formation of the Grand Canyon and some other amazing national park landmarks. However, human disturbance also accelerates soil erosion, and some examples around this include mining, recreational activities, construction zones, and farming. We found that the geologic rate of erosion compared to unintentional and intentional erosion caused by man has drastically increased, especially once we became civilized and started using equipment and started intensively farming. And we saw those rates drastically increase just before 2008. The amount of lake sediment has increased drastically since 1830 to when it stopped being measured in 1996, although I'm sure they're still measuring it. We just don't have the data. So we saw quite a bit of sediment going into the Minnesota River, to which about 92% was attributed to agriculture. And then we saw about 42% of agriculture contributing to the sediments in the upper Mississippi and St. Croix rivers. The rest were due to most likely construction, mining, etc. So let's talk about soil loss tolerance, the T value. So the T value basically is the maximum rate of annual soil loss from water and wind that will permit crop productivity to occur economically and indefinitely. A T value for most soils is between 2 to 5 tons per acre per year of soil loss. That's the normal amount. So what does tons per acre mean? Well, about 1 acre, 6 inches deep, is equivalent to 2 million pounds of soil. So if we take about 6 inches of soil, that's about 1,000 tons per acre of soil. 1 inch of soil basically equates to 167 tons of soil. So if we're losing 10 tons per acre per year, what essentially is time per inch? Ultimately, we are losing 16.7 years per inch of soil that we lose. So this is obviously not sustainable. How our land is used is kind of broken up in this graph. So we've got 402 millions of acres in federal lands, 377 millions of acres in cropland, 32.7 millions of acres in CRP land, which is basically a USDA conservation program for soils. We have 120 millions of acres in pasture land, 406 millions of acres in rangeland, 407 millions of acres in forest land, about 51 somehow being utilized elsewhere, and about 98 million acres that are developed. So when we talk about the magnitude of the erosion problem in the United States, we have about 377 million acres of cropland. That's about 25% of the United States. More than 50% of all water erosion is from cropland, unfortunately. And the average loss on cropland is about 3.1 tons per acre per year. That's about 56 years of production that we're losing per inch lost. So we have some graphs here showing the annual average soil erosion by water on cropland and CRP land. Now remember, CRP land is basically in protection. It's in a conservation program for erosion control measures, essentially. So this map shows from 1982 to 1997 that due to increased CRP program usage, we drastically reduced annual soil erosion loss by water. So this program is working, which is great. We're trying to solve the problem and it's working. That's always good news. However, there are other problem areas that we need to address, such as poor forest management, poor pasture and range management, urban construction zones, and surface mining are all great contributors to soil erosion issues. We're also losing a lot of land to development, which means that we're going to have a lot of impermeable surfaces with water coming over them, which can erode further soil down the road. So let's talk about the erosion process. There's three related processes to erosion. Remember, this is one of your learning objectives. So the first is detachment. Water hits the soil and causes it to detach. It's like a little miniature explosion as shown in the upper right-hand picture. And then all those soil particles that were detached are then transported and deposited elsewhere. So the three related processes are detachment, transport, and deposition. Splash erosion on bare soil is the first form of water erosion, as shown here in this image. It literally hits the Earth's surface like a fist, causing that soil to have like a miniature explosion that causes it to detach. We also have surface runoff or sheet erosion, which is the transport of detached particles. Clays and silts travel the furthest, and sand travels very little. We also have channel erosion, which causes rills and gullies and stream bank erosion. A rill is decently small. You can see rills in the image on the left going down the hillside. They're usually about like a foot or less wide. Gullies are significantly larger, as shown in the picture on the right. Forms of water erosion include sheet erosion, which leaves behind these little pedestals shown in the top right. Rill erosion, which again leaves behind small channels about a foot or so wide. Rill erosion, gully erosion leaves behind giant channels about the size of a pickup truck. So these are detrimental, especially. And so essentially, sheet erosion turns into rill erosion, which turns into gully erosion. So anytime we see the start of any of these, we want to make sure that we address it and stop it immediately. Some of the factors affecting erosion include rainfall characteristics, soil characteristics, slope characteristics, and vegetative cover. This is another one of your learning objectives. So rainfall characteristics essentially talk about effective rainfall. What is the frequency, intensity, and duration of rainfall? As these increase, total energy available for erosion basically increases as well. Soil characteristics like texture, structure, organic matter content, and permeability also give rise to whether or not soil is susceptible to water erosion. For example, textures that are high in silts and clays are going to be more susceptible to water erosion. Soil structure that has very little organic matter to glue it together is going to be more susceptible to water erosion. Also, poorly formed soil structure that doesn't allow faster infiltration causes more water to run over the surface of the soil, and that also gives rise to more water erosion, which leads us to permeability. Slope characteristics are important. The length and percent slope is going to give rise to erosion. Vegetative cover basically helps to decrease detachment, decrease transport of soil particles, and then decrease deposition. Vegetative cover also essentially gives soil. The effects of erosion include those on-site and off-site. Some on-site effects that can affect soil productivity include a reduction in topsoil depth, reduced rooting zone, lower nutrient and water holding or supplying availability, and loss of the fine fractions such as silt and clays from topsoil. Some offside effects of sediments basically include the fact that sediments are the number one pollutants of surface waters. They negatively affect water quality and they destroy aquatic habitat. You can see here where you have sediment-laden water coming in from a tributary and into the clear water of the actual river. And if you get too much sediment coming into a body of water, it basically brings along with it a lot of attached nutrients, and they're kind of attached like a post-it note. They're only temporarily attached, and so they're able to detach in the body of water And excessive amounts of nitrogen and phosphorus cause something called eutrophication. It essentially causes mass algal blooms, as shown in the picture on the bottom right. And as those algal blooms deteriorate, as they're broken down and degraded by microorganisms, all of the oxygen will be sucked out of the water, and it results in mass fish kill. Some more sediments. In the Yellow River in China, there's 1.6 billion tons of sediment per year lost. They lose about 18 tons per acre per year. The Ganges River in Indiana, or I'm sorry, in India, about 1.5 billion tons per year is lost. The Mississippi River in the United States, about 300 million thousand tons per year is lost. The best soils in the United States and in the world are literally being flushed down the Mississippi River. Let's talk about some offside effects, such as road and hill slope failures. Now, these put lives at risk. Here you can see where a road has washed out along a cliffside, or housing developments built into hillsides have been destroyed, causing loss of life. In the Lock and Cheetah landslide in California, we discovered the ultimate cost of beachfront housing when developers cut into the toe slope of an unstable and steep hillside. Essentially, they cut the foot off of the mountain, and in order for the mountain to stabilize itself, this giant mass moved down to become the new toe slope. However, there were houses there, and it happened in the middle of the night, and many people were killed. So this is a great example of why we want to make sure that we understand how soil works, the stability of a slope works, before we start engineering our own way through it, because Mother Nature will always win. There's some examples of Indiana erosion here. On Levee Road, the Whitewater River near Brookville, Indiana, there's 3 images that illustrate the evolution of a portion of the Whitewater River near Brookville. The first 2 images show that between 2005 and 2008, the river moves between 330 and 365 feet closer to Levee Road. This is highlighted at the end of each arrow. And the third image, collected on a field trip to Levee Road in May of 2011, documents that the channel continued to migrate in the direction of the cut bank and undermine Levee Road, leaving it impassable. The road was repaired by August 2012. It's important to note that these images represent extreme examples of river erosion in Indiana. We use them because they make the erosion process easier to see. Many Indiana rivers are essentially stable or change very slowly. So here you can see the Levee Road and the picture on the upper left. And in the picture on the lower right, you can see the river moving drastically closer to the road. You can really see the shift in the extent of the cut bank towards the road relative to 2006 in the bottom right picture compared to the top left. And here's the third picture showing the actual cut bank as it moves towards Levee Road. And it will continue to migrate in that direction, causing significant erosion and leaving it impassable. In the White River near Centerton, Indiana, there's 2 images that document a cut bank located on the White River. It's migrated 290 feet to the northwest within a 5-year period. That's pretty quick erosion. In addition to the agricultural land that is lost to the river, notice the existing utility poles threatened by future fluvial erosion. So here you can see in the upper left, the White River near Centerton, Indiana in 2005. The red line indicates location of utility lines to the northwest of the active river channel. And in the bottom right, you can see the same river location in 2010. The river has moved approximately 290 feet to the northwest and is threatening both agricultural land as well as utility lines. The same river location is shown here in 2012. The cut bank has continued to erode towards the utility poles and lines. And it's not looking so promising for that utility pole, is it? So there's further articles on Indiana erosion. There's an article on the erosion of the Ogden Dunes in Portage, Indiana, along Lake Michigan. And there's some contractors hired in Richmond, Indiana to install erosion control measures along the White River at the intersection of 2 highways. But let's talk about the prediction of soil erosion by water using the Russell equation. The revised universal soil loss equation is what Russell stands for. It's an equation that's used to predict the loss in tons per acre per year as a function of rainfall, soil type, landscape, vegetation, and conservation practices. It's basically A equals R times K times LS times C times P. And we're going to learn what each one of these things is. You won't be expected to calculate the Russell equation, but you will need to define each of the variables. A is equal to the soil loss in tons per acre per year. R is equal to the rainfall factor in energy per acre per year. K is the soil erodibility factor in tons per energy. LS is the length and percent slope factor. C is the crop and vegetation management factor, and P is the conservation structures factor. Let's talk about each of those individually. The rainfall erosivity factor, or R, is the driving force for sheet and rill erosion. The average annual energy from rainfall events, including the amount, intensity, and seasonal distribution, is taken into effect. So for example, in Kentucky, this ranges from about 150 to about 250. But in Lexington, Kentucky, it's 165. But far west Kentucky, the rainfall erosivity factor is 250. Where's the most erosion going to occur? It's going to occur in the rainfall erosivity factor that's higher. Here's what the R factor's isoerodin map looks like for the east portion of the United States. California and the west coast basically has its own map. But you essentially see all these squiggly lines. You would find the values over on the right and follow them over to your county of residence. The K factor is the soil erodibility factor. Soil's inherent susceptibility to erosion is determined by this factor. It indicates the amount of soil lost per unit of erosive energy in rainfall. It's measured as the rate of soil loss from a plot 22 meters long with 99% slope and kept continuously bare by tillage. Basically, some of the worst case scenarios. The factors affecting this include texture, organic matter, structure, and permeability. This value ranges from 0.15 to 0.5. And sandy loam, for example, could be rated at 0.20. Loams to clay loams would be rated about 0.32. Silt loam in loess is rated about 0.49. The LS topographic factor is calculated as the amount of soil lost from a plot relative to a standard plot. Again, 22 meters long and 9% slope. What happens as length increases or as slope increases? Well, as length and slope increase, the topographic erosivity will increase, especially as related to length. These values can range from 0.2 to greater than 12. The C factor refers to cover and management. It depends on the amount of tillage and the amount of surface residue left. The more residue, the less problem. So this can range from 0.001 for undisturbed forest all the way to 1, meaning fallow, no residues there, very high erosivity. As you can see in the graph on the right, interill erosion increases drastically the less ground cover we have. We see almost no interill erosion development with 60 to 80% cover. Support practice factors help diminish erosivity. This is calculated as the ratio of soil loss with a given support practice to the corresponding loss of row crops, as if they were planted up and down the slope. This includes terraces, which have a value of about 0.5, contour tillage, which has a value of 0.5 to 0.9 depending on the slope, strip cropping, and which basically has alternating strips of grass and row crops across the slope. And if there's no practices, then it gets a value of 1. Our goal for land use planning is to manage the A value to be less than or equal to our T value. Remember, an acceptable T value is between 2 and 5 tons per acre per year. Conservation farm plans use Russell to evaluate different management plans, and this has been the basis of the conservation advances in the last 30 years. So let's talk about the 3 principles of erosion control. We want to reduce raindrop impact on the soil surface. We want to reduce runoff volume and velocity, and we want to increase soil's resistance to erosion. Remember, these are principles, not practices. I'm going to give you my guide to success. If you're managing a slope, you want to manage the top and the toe. Manage the water coming on site from the top and manage the runoff from the site at the bottom, and you'll always be successful with erosion control. Practices to reduce soil erosion include no-till, ridge till, strip till, mulch till, and reduced tillage. No-till is when soil is left undisturbed prior to planting, which occurs in narrow seed beds 2.5 to 7.5 centimeters wide. Weed control is primarily done by herbicides. Ridge tills are when soil is undisturbed prior to planting, which is done on ridges 10 to 15 centimeters higher than row middles. Residues moved aside or incorporated on about 1/3 of soil surface. Herbicides in cultivation is used to control weeds. Strip tillage is when soil is undisturbed prior to planting. Narrow and shallow tillage in row using a rotary tiller, in-row chisel, and so on. Up to 1/3 of soil surface is tilled at planting time. Herbicides in cultivation are used to control weeds. Mulch tillage is again when soil surface is is when soil surface is disturbed by tillage prior to planting, but at least 30% of residues left are on or near the soil surface. So basically 30% of the residues are left behind. Tools such as chisels, field cultivators, discs, and sweeps are used. Example would be stubble mulch. And herbicides in cultivation are used to control weeds. The stubble left behind helps to provide a protective cover for soil. Reduced tillage is any other tillage and planting system that keeps at least 30% of residues on the soil surface. Practices to reduce soil erosion in agriculture sites. What can we do to prevent this? Contour plowing and terracing is very helpful. Contour plowing is cultivating along curved lines that go around the hill at a fixed level. Contour plowing slows down the runoff of soil water from the land, and terraces keep water from the hillside. The water is absorbed and does not follow directly downhill. It also prevents soil from moving downhill. Planting trees around farmlands also helps. Farmers plant rows of trees as windbreaks to surround big areas of farmland. These trees protect the farm from the wind that causes erosion. Some important terms for you to understand include contour intervals, which is a vertical distance between adjacent contour lines. Index contours is the amount of the contour interval given in the marginal information. On most maps, the contour lines are printed in brown. Starting at 0 elevation, every fifth contour line is drawn with a heavier line. These are known as the index contours. Other practices to reduce soil erosion in agricultural fields. Strip cropping, crop rotation, and buffer strips are all useful. Mulch till and ridge till are also useful. Maintaining vegetative cover, reducing tillage intensity, improving soil characteristic, and using structural practices are all important parts of reducing erosion in ag lands, such as contour farming, providing windbreaks, residue management, and grassed waterways. On a 12% slope, with a switchgrass hedge every 16 meters across the slope, receiving 120 millimeters of simulated rainfall, soils that had conventional tillage with corn residues removed had significantly greater amounts of soil erosion and water runoff compared to conventional tillage where the corn residues were not removed or no-till, which all had significantly smaller amounts of soil erosion and significantly smaller amounts of runoff. The influence of conservation tillage on soil biological, chemical, and physical properties must be noted because it's very important. As we conserve the amount of tillage that we use, we see organic matter levels increase, earthworm numbers go up, macro porosity increases, aggregation goes up, infiltration and percolation both improved, soil water holding capacity is enhanced, nitrate leaching increases, which is not a good thing. Soils become cooler and wetter, which can be a negative in the spring. They may have more immobilization and denitrification, which are also not good things, and surface pH may drop. But other than these last four negatives, it's looking like conservation tillage has been very beneficial for soil biological, chemical, and physical properties. More practices to reduce soil erosion include buffer strips, where we minimize sediment influx into riparian zones and waterways by providing a grassed waterway along a field or riparian buffer. These vegetation filters filter out incoming sediment from surrounding fields. They're like little waving fingers protecting any nearby stream or river. So this is a farm showcasing several conservation practices. They may use tillage in their fields, however, they have windbreaks, filter strips, grassed waterways, a wetland restoration, and riparian forest buffers. All wonderful conservation practices that are leading to healthy waterways nearby. What can we do in residential areas to help decrease the amount of sediment that ends up into our water? Well, we can have a garage with a green roof or driveway with permeable pavers. We can have roof downspouts to rain gardens or to a dry well or to a rain barrel or a cistern. Remember, erosion is an infiltration splash problem, so if we can protect soils and provide vegetation as filtration for water before it can hit impermeable surfaces, remember, we always want to protect our top and toe. We can utilize all of these things to be aware of surrounding gutters and streams as well. Other practices could also include terrace gardens on steep slopes, vegetative buffers along edges of impermeable surfaces, roof downspouts to deposit water into rain gardens, and permeable driveways. Construction sites practices to reduce soil erosion include hydroseeding and bioengineering, utilizing silt fences to catch particles before they can leave the site, or directing anything that comes off site into a sedimentation basin that can be scooped out and replaced. Utilizing geotextiles has been a marvelous way for beachside resorts to maintain the integrity of shorelines. Pavers are a great way to maintain integrity of driveways. It allows for the surface to be permeable while still providing a driveway structure. They are very expensive though. In this graphic, you can see a variety of erosion control practices. You can see a water berm directing water into a slope drain erosion control blanket that then goes into a variety of trees. We can see ditch checks that help move runoff into a slope drain geotextile fabric rundown liner. We have a rock spillway that takes water out of a sediment trap. We have a diversion berm helping to move water into these catchments. We have contour diversion ditches to help move water across slopes. And over the road, we have water moved into a pipe slope drain that moves the water through riprap and a silt fence. If you love this topic and want to learn more about erosion control and how to save the world, consider taking NREM 427 this spring.